And we are recording. Hello, hello, hello. Hello, YouTube.
Garcia, you forgot to finish handing it out.
Did I? I'm sorry. Oh, you have to write your own test. That's the first part. All right. Did I get you two? Did I get everybody? Huh? Okay, we're not doing that right now. No stage today. Okay, we're flying without a net today. You trapeze artists, you. All right, go straight to number one. We're going to take our time with this. This is probably going to take today and tomorrow. All right, but you're expected to be able to do this on Friday in one period. Here we go. Part one. Converting from octal to decimal to ternary or trinary, back to decimal, back to octal. You are the Harvard Mark I. Be one with your inner computer. You are the Harvard Mark I. Grace Murray Hopper feeds you 2 punch cards, inputting the numbers A and B. A is 13 octal and B is 61 octal. Question 1. Convert it from octal to decimal. Display your input to the screen, to the console. Remember that the computer talks to humans in decimal, right? But this computer does its work in octal. Okay? Well, no, I take that back. It stores its work in octal and it does its work in trinary. Okay? So, let's do it. Hang on. So, let's take the number A, which is 13 in octal, and convert it to base 10. How do you do that? How do you convert to base 10? You look at the placeholders and you multiply. 3 times what place? And 1 times what place? So it's 8 ones plus, no. What place is it?
1-8.
Yeah, 1-8. No. No, you getting what? Yeah, it's 1-8, right. Sorry. Okay. You got 1-8, 1 in the 8's place plus 3 in the 1's place. Work that out and you get 11 in base 10. Okay. That's number A. Number B is 61 octal. Let's do the same thing. 61 octal. How do you convert that to base 10?
1-8.
Well, 1 in the 1's place and 6 in the 8's place. So 6 eighths plus 1 1 is how much? 6 times 8?
Oh, yeah. It's 48.
It's 48 plus 1? 49. Okay. That's question 1. You are done. Question 2. Convert this input so you can work at it at the tube level. Remember the Harvard Mark I had tubes instead of chips and did arithmetic in base 3, not base 2. So let's convert these numbers to base 3. How do you convert 11 to base 3 and 49 to base 3? Hang on. Right, dividing. So question 2. How do you convert 11 from base 10 to base 3? You take 11 and you divide it by 3 and look at the remainders backwards, remember? So 3 into 11 goes at most 3. Remainder is 2. And then 3 into what? No. 3 goes 1. Remainder? 0. And 3 into 1 goes 0. Remainder? 1. And when you hit the 0, you're done. So what's the answer? How do you write it? 102. Right? Because it's 2 1s, no 3s, and a 9. Does that work out to 11? Right. All right, do the same thing. What was it, 49? Yes. What's 49 in decimal when you convert it to base 3? So take 49 and do what? Divide by 3. So 3 into 4 goes once, remainder 1. 3 into 19? 6 remainder? Because it's, wait. All right, do I have to write it out? 3 times 1 is 3, minus, you get 1, bring down the 9. 3 into 19 goes 6 because that's 18. Subtract, and you get 1. So that's the remainder, right. All right, now you go 3 into 16 goes at, wait, hang on. 3 into 16 goes at most 5. And the remainder is 1. And 3 into 5 goes 1. Remainder 2. And 3 into 1 goes 0. Remainder. So what's the answer? 1, 2, 1, 1. 1, 2, 1, 1. Are we okay with this? Alrighty. Is it all ready yet? All right, so are you ready for number 3? Is this hard? No. It looks a lot like this, yeah. Make different numbers. We'll change the numbers to protect units and problems. All right. Nobody knows Dragnet anymore, but it's okay. You can use a real graphing calculator, a TID 384, or a virtual graphing calculator if you're stuck with the arithmetic, but you're not using Sage. What? You could play around with logs. I'm not going to talk about that yet. What? Cliff?
I'm having trouble with this.
Why? What part?
This is not making sense. Binary is way easier.
Binary is way easier. Yeah, I know. That's why we're doing trinary. You have to know how to do this in any base. What?
So,
Yeah, sure. You need lights? Go on the lights. You want the lights? No? Okay. Yeah, not the book one, though. That one's broken. I guess so.
what are the places?
The places, all right. What are the places in base 3? Let's see. The 1's place, the 3's place, the 9's place, the 27's place. Whatever. It's not, that doesn't work either. See, I knew something's broken. All right, amazing. All right. So whatever base you're in, you always start with the 1's place, right? Then you multiply by the base. 1 times 3 is the 3's place. 3 times 3 is the 9's place. 3 times 9 is the 27's place. Does that work out? A 1 and a 3 is 4. And 2 9's? 18 and the 4? 22. 22 and how much? 27 plus 22, is that 49? Yeah, it works. All righty. So, are you ready for question 3? Question 3 says, add A and B in trinary. The way the computer used to do that in the Harvard Mark 1. All right, so I'm going to take 102 plus 1211, right?
Put the 1211 up top.
You can put it on top. It doesn't matter when you're adding, but when you're subtracting, yeah. Because look at how they said it. Do B minus A. B is bigger, right? So when you subtract, it's going to be important to do that. When you add, it won't be that important. All right, so 3. We're going to add 1. What the heck was it? 1, 2, 1, 1? 1, 2, 1, 1, and 102? Okay. So this is A plus B. All right, now this was A and this was B. The order doesn't matter. So how do you add? Now, we're adding in base 3, remember. So 2 plus 1 is, don't say 3. 10. Good. Because whenever you carry or borrow, I don't care what base you're in, you always carry or borrow 10, because 10 in base 3 really means 3. There you go. So 2 plus 1 is 10. Freak out your math teacher today. Do that in math class, all right? 1 and 1 is 2. Because remember, what are the legal digits? You're only seeing what digits here? Zeros, 1s, and 2s, right? All right, 1 and 2 is 10. Carry the 1. And 1 and 1 is 2. Perfect. All right, now we're going to go through steps 4 and 5. It'll actually be a check. So I'm not going to check this yet. All right, now do B minus A. B being the bigger number, because we're not talking about signed numbers yet, minus A. Here it is important to write the 102 on the bottom, because we're not dealing with signed numbers yet. Remember the signed numbers we did yesterday? That's the last page, okay? Don't do any of that stuff until the last page. All right, so subtract. You can't take 2 from 1 until it's greater than or equal to 2, so you look at the 1 in the 3's place, leaving 0 3's, bringing over 10 1's, combining with 1 1, 11 1's minus 2 1's is what? What? How about 2? Okay.
Wait, what?
What? Who? Where? Who? What? Because think, guys, this is like a foreign language, right? Think, you're in Spanish class, right? What does your Spanish teacher do? Hay que pensar en español. You're gonna do it all in Spanish. Well, here you're doing it all in base 3. 11 doesn't mean what you usually think of as 11. 11 means a 1 in the 1's place and a 1 in the 3's place. So that's a total of 4 minus 2 is 2. I told you it was easy.
See, I didn't know that.
Right, you gotta think in base 3. All right, 0 minus 0, well, that's easy. If you don't have to borrow, you're done. What is it? 0. And 2 minus 1 is 1. And 1 minus nothing is 1, and you're done. Now, I could check this, but I'm not going to check it because steps 4 and 5 will actually be checking it for you. All right, so are you ready for 4? Any questions how we add or subtract in base 3? All right, this is exactly how the Harvard Mark I that Grace Marie Hopper was programming, that's how it worked. Remember, it did a total of how many calculations a second? 3. There's 2 of them per second. That's it. That's all you get. 3 of these per second. The Harvard Mark I is faster than you? Is that what you're saying? That's sad. Okay. Now, question 4. Can you convert these answers back to base 10 so the computer will display the answer on the screen in base 10? Well, you have no 1s. You have 2 3s. So let's write that. 2 times 3. You have no 9s, but you have 2 27. So 2 times 27. All right. So what's 2 times 27 anyway? 54. And 2 times 3 is 6. So the total is 60, and that's in base 10. Does that make any sense? Look at the very beginning. What happened? 61? 2 3s is 6, and 2 27 is 54. No, it's got to be 60. Now look, does this make any sense? Look at, where is it? We converted them to 11 and 49 in base 10, right? So what if you add them in base 10? What do you get? You get 60. Isn't that what we just said? Oh, there's your check. It works. All right, let's convert this guy. You got 2 whats? 2 1s, no 3s, 1 times 9, and 1 times 27. So what is 27 plus 9? 36 plus 2? 38. All right, so 27 plus 9 plus 2 is, I already forgot, 38? Now, is that what you get if you actually subtract them in decimal? What is 49 minus 11?
38.
So does it work?
Yes.
That's a check. Okay. Now remember, this computer does all its arithmetic nice, neat, and fast and efficient and whatnot in base 3. But to save space, when it stores the information on punched cards, we didn't even have disks then. It stores the answer in octal like we started. Remember? Didn't Grace Marie Hopper feed the computer a punched card with the input? That card, that's your storage device. That's like your disk or your stick, right? It doesn't hold a lot of information. So once you're done with this, how do you store this back on the punch card? You convert it to octal, right? That's it. This computer stores stuff in octal and operates with numbers in base 3. So how do you convert 60 from base 10 to base 8 is really the question. That's number 5. How do you take 60 from base 10 and convert it back to base 8 so you can store your information? Divide. So 60 divided by what? 8. Good. So 8 into 60 goes at most? 7. Remainder is? 4. All right. Then 8 into what? 7 is? 0. Remainder? 7. So what's the answer? 74. Which you could check if you go back to the very beginning and you actually add the octal numbers. What's 3 and 1 in 3 1s and 1 1 in base 8? What's 3 1s and 1 1 in base 8? 4. And what's what is it? 1 in the 8th place and 6 in the 8th place. What do you get in the 8th place? What's 1 plus 6? 74, right? Now, is that what we got? Okay, questions? Did I miss a question somewhere? No? Good? Okay. All right, but wait, we're not done. We also have to convert to 38. 38, right? The difference, the subtraction problem. So how do you convert 38 from base 10 to base 8? Divide by 8. Let's do it over here. 38 divided by 8 goes at most what? 4. So the remainder is 6. And 8 into 4 goes at most 0. Remainder 4. So the answer here is 46. And again, if you go back to the octal, where's the octal? And you subtract, let's do it over here. 13 in base 8 from 61 in base 8. Yeah, that's a weird 6. Go away. This is hard to do on a tablet. 61 base 8 minus 13 base 8. Are we going to get the same answer? Let's see. Let's do this in base 8. What's 3 from 1? Remember the Tom Lehrer new math song? You can't take 3 from 1 until it's greater than or equal to 1. So you look at the 6 in the 8's place. Leave 5 8s, bring over 10 1s plus 1 1 is 11 1s. Minus 3 1s is 6. Because you've got to think in base 8. A 1 and an 8 is 9. Minus 3 is 6. And 1 from 5, since you don't have to borrow, it's easy. It's what? 4. Is that what we had as our final answer, Regis? Let's see. And 46. Here it is. Yep. Okay, so are you good at being Grace Murray Hopper in the Harvard Mark I? Okay, now let's go to more modern computers. Page 2, are you ready? All right. Now we're going to convert from hex, which is what modern computers store information as, to decimal, where the answer is displayed on the screen, to binary, so we can add and subtract at the chip level, back to decimal to display the answer on the screen, back to hex to store your information on the disk. Yeah. Just like this. It's Friday. It's Friday. We're going to continue this tomorrow. All right, so you are the first IBM PC, and Bill Gates feeds you a floppy disk inputting the numbers. A is 71 hex. It's the same question, but now we're doing hexadecimal to start. All right, so this is question 6. You are being inputted 71 hex, that's number A, and A5 hex, that's number B. Can you convert them to base 10 so that the input is displayed on the console, on the screen? So how do you convert 71 from hex to base 10? You multiply by the placeholders, right? So you have 1 what? 1 1. And you have 7 what? 7 16s, right? Hexadecimal means 16, base 16. What is 7 times 16?
112.
Right, 70 and 42 is 112. Plus 1? 113. Okay. Now also convert A5 from hex.
A is 11, right?
A is, well, not 11, careful. It's 10, right? Right after 9. All right, so I got 5 whats? 5 1s. And what? How many 16s? 10 16s. That's easy. 10 times 16 is 160 plus 5 is 165. That's question 6. You are done. That's what the computer does. You input that stuff, you load it from the disk, it gets displayed as 113 on the screen and 165 on the screen. Because the computer talks to you on the screen in base 10. All right, number 7. Convert this input so you can work with it at the chip level. In other words, convert the decimal numbers into binary. Actually, there's an easier way. Don't we know a shortcut to go from hex to binary directly?
Yeah.
You could do this. What could you do? How do you convert 113 base 10? How do you convert 113 base 10 to base 16? You divide by the base 16 and look at the remainders, right? But don't we have a quick way of going from hex to binary directly? Every digit in hex is represented at most by how many bits? 4 bits. So how do you write 1 in 4 bits? 0, 0, 0, 1. How do you write 7 in 4 bits? 0, 1, 1, 1, 1, 1, 1, 2, 1, 4. Right? Do it again. How do you write 5 in 4 bits? 0. Do you need an 8?
No.
Do you need a 4?
Yes.
Yes. Do you need a 2? No. Do you need a 1? Yes. Okay. Now I want to convert how much?
Oh, 10.
A is 10. How do you write 10 in 4 bits? Do you need an 8?
Yeah.
Yeah. Do you need a 4?
No.
Do you need a 2? Yeah. Do you need a 1? No. There you go. That's the binary version of 71 hex.
But it's 1, right? It's 8 digits.
You can write with the 0 in front or not. This is 10100101. Write it all together. You don't need the spaces. You can space it out if you want. And you don't have to write the 0 in front if you don't want to. It's 01110001 or 111001, right? 001. All right, so now you can be one with the chips. At the chip level, we add and subtract in binary. And isn't that what number 7 is about? Yeah.
When you did that, were you doing that with 71?
Yeah, this one here is 71. This is the 1. This is the 7. This is the 5. This is the 10. Now, if you're not happy with that, remember, you know how to do it by dividing by 16. Look at the remainders. Just divide this by 16 as many times as it takes to get 0 in the quotient, and then write the remainders backwards. You're going to get the same thing. It's just a lot of dividing. Look at this. It's going to be 7 steps, and this is going to be 8 steps. It's going to take a while. Dividing by 2, right, takes a while. All right, so I'm not doing it that way. So that's question 7. Sorry. Now 8. 8 says add them up. All right. What is 1010? 0101 plus, it says do A plus B, right? This is B actually. Plus A, 1110001. All right, remember, think in base 2. Scrolling up. Wait, hang on. Why can't I find the edge of this? My screen is screwed up. There it is. All right, is that good or more?
Yeah.
All right, there you go. All right, be 1 with base 2. That's funny. What's 1 plus 1? 10. Carry the 1. 1 and nothing? 1. 1 and nothing? 1. Nothing and nothing? 0. Nothing and 1? 1. 1 and 1? 10. Carry the 1. 1 and 1? I'll skip the nothing, right? 10. Carry the 1. 1 and 1? 10. That's an answer. Don't worry about dropping the highest bit. That's with signed numbers. I'm not doing that yet. Okay? All right, so there's my sum. How do you do the difference? B minus A. The bigger one is B. Is this 101001 minus A 1110001. Okay. Are you ready to subtract? 1 minus 1, 0. 0 minus 0, 0. 1 minus 0, 1. 0 minus 0, 0. 0 minus 1 you can't do until you borrow. So this becomes 0. You bring over 10. And 10 minus 1 is 1. Base 2. This means 2. All right, so 1 from 0 you can't do, so borrow. But you can't borrow here, so you borrow here. What's this become? 0. And then you bring over 10. But I wanted to borrow over here, so I'm going to take 1 from 10, leaving not 9. 1, and bring over 10. So there's a 1 here, a 10 here, and a 0 here, right? 10 minus 1, 1. 1 minus 1, 0. 0 minus nothing, 0. You could write the 2 zeros here if you want, but I'm not going to. All right, that's number 8. Question? Any problems on number 8? We are out of time, are we not? All right, we're going to finish this off. We're on number 9 tomorrow. All right, let me store this so we can take it from here tomorrow. All right, we're going to convert to base 10 the answers so that gets displayed on the screen. And we're going to convert the base 10 numbers or even the binary numbers to hex to store the answers to disk. And we're so good at this, it's scary. File, save as. Chapter 5, yeah, on the desktop. Bing. Okay. And that's the end of that. And that's the end of that. Bye-bye, YouTube.